Assalamualaikum warahmatullahi wabarakatuh and good day. So in this video, we will learn chapter 2, continuous random variables and their probability distribution. So last week, previously you have learned chapter 1, which is discrete random variables and their probability distribution. So you learned what is random variables, what is discrete random variables, and you can see commonly used discrete random variables and their probability distribution, and then the mean, the variance for the commonly used distribution, and then you learn the expected for mean, expected for variance, and then you learn moment generating function and Chebyshev theorem. Okay, so today in chapter 2 you also you will learn quite the same concept, okay, but now we focus on continuous random variables and their probability distribution. So this is the expected outcome, okay, but maybe in this video we only cover for outcome number 1 and 2, okay. So this is the content, okay. You have 2.1, 2.2, 2.3 and 2.4. So in this video I think we will until 2.1 and 2.2. Okay, so the probability distribution function for continuous random variable. So at the first place, you must understand what is continuous random variable. So continuous random variable, a random variable that can take on any values in an interval is called continuous. Okay, so for example here, yield of an antibiotic in a fermentation process. That means the measurement of yield of antibiotic. How many milliliters? Okay, daily rainfall at a specific geographical point. For example, at Quantum, how much is daily rainfall? And then height, weight, salary, price, and etc. Okay, so you can differentiate between discrete random variable and continuous random variable. So basically, in continuous random variable, you can take decimal point value. Okay, that's why it's continuous. For example, my height 1.53 meter. Okay, so it can be 1.53467 meter, for example. So you can see there are many decimal places. Okay, so that is a continuous random variable. Okay, now look definition 4.1. Let y denote any random variable. The distribution function of y denoted by capital Fy here is such that Fy equal with probability y less than equal with y value. So this is the value. And this value is between negative infinity to infinity. So look example 4.1. Suppose that y has a binomial distribution with n equal to 2 and p equal to half. Find Fy. Okay, find the distribution function. So if you look, we have n equal to 2, p equal to 0.5 or half. Okay. So what is the distribution function for py? I mean the density function for binomial. You have n over y, p power y, q, n minus y. Your y is 0, 1, 2 because you have n equal to 2. Okay, so this density function you must remember. Okay, so it will be 2y p p is 0.5 lah. Okay, 0.5 y, q is 0.5 as well. Y 1 minus 0.5, so you get 2 minus 1. So this is the distribution function, but what is the value? So when py equal to 0, you get 1 over 4. When py equal to 1, you get half. And then py equal to 2, you get 1 over 4. Okay, basically if you do the distribution function, you will get 0, 1, 2. So 0 is here, let's say 1 over 4, 1 over 2, 3 over 4, 1. Okay, so 0 you will get 1 here, and then 1 you get half, and then this is py. Okay, this is py, not capital Fy. Capital Fy is a cumulative. Okay, so 2 is another half. Okay, so you will get this one. You remember when you do the histogram too, you get like this lah. Okay, so that's the density function, distribution function for binomial. Okay, so let's say if you have f negative 2, so what will be? Okay, based on the definition, this one will be f, probability y less than negative 2. Okay, and basically if you look here, okay, if you look graph ni, when any y which is less than 0, it will get 0 lah. Here, probability 0. Okay, because y only assigned for 0, 1, 2. You have 1 over 4, 1 over half, and 1 over 4 here. Okay, that's why we consider when we have negative 2, this one become 0 because it will be at this side. Okay, so we can consider that Fy will be 0 for any y less than 0. Okay, because from this graph. Okay, so let's say if one f 1 over 5. Okay, if you look 1 over 5 also, it's less than or equal 1.5. Okay, it will be like this lah. Okay, if you solve f 1.5, this one should be p y less than 1.5, isn't it? So based on here, you can see that you have p y equal to 0 plus p y equal to 1. So this one basically you will get 1 over 4 plus 1 over 2. So you get 3 over 4. Okay. So that's why when you draw the figure, okay, when we have fy is a cumulative distribution function. So this is your y. So that's why you can see that when y equal to 0, okay, you will get 1 over 4 lah here, isn't it? Here, 1 over 4. This is 0, 1, 2, 3. For example, here can be negative 1, negative 2. Okay, so based on this one, when you have negative 2, y less than 0, it gives you 0 probability. Okay, but when you have y which is less than 1.5, 1.5 is here, so consider this one, you will get 3 over 5. Okay, this is 1 over 4, 1 over 2, 3 over 4, 1. Okay, it will be here. This one is 0 lah. Okay, 0. And then the last one, 3, you will get 1. That's mean when y greater than 2, okay, your fy will become 1. Okay, for any value which is y greater than 2, which is the side, you will get 1 here, the probability. Okay, that's why you will get this step function. Okay, because you have binomial distribution, which is we know is a discrete. But when you want to find the distribution function by using the continuous random variable method, you will get step function like this. Okay, that's why any y which is less than 0, you will get 0 probabilities. But between 0 and 1, you get 1 over 4 probabilities. When you have 1 and 2, you get 3 over 4 probabilities. And any value which is greater than 2, you will get 1 probabilities. So that is a distribution function. When you have binomial, and then you use continuous random variable to solve the distribution function. Okay, so you will get step function. So for continuous random variable, we have theorem 4.1. So this is the properties of a distribution function. So if fy is a distribution function, then you will get the first one, any negative value, okay, negative value y or x here, you will get limit from y goes to infinity, your distribution function will goes to 0. Okay, number 2, if you have y equal to infinity number, okay, positive number, the limit for fy will be equal with 1, because this is a probability. Your value should be between 0 and 1. So any number, negative value, it will convert to 0, and then any number with positive value will give you equal with 1. Okay, and then the distribution function for y is non-decreasing function. Okay, its step of function is going to the right, increasing and increasing, okay, of y. If y1 and y2 are any values such that y1 less than y2, then the density function or the distribution function y1 will be less than y2. Okay, so that's why we call it non-decreasing function. Okay, not decrease, increase. Okay, and now we have definition 4.2. A random variable y with distribution function fy is said continuous if fy is continuous for y between negative infinity to infinity. Okay, definition 4.2 quite similar with 4.1, but here you must look, okay, a random variable y with distribution function fy is said to be continuous, okay, is continuous if fy is continuous. That's mean if fy is continuous, so fy for y is continuous, whereas your y is between negative infinity to infinity. Okay, so then you have another definition 4.3. Okay, let fy be the distribution function for a continuous random variable. So now you know y is a continuous random variable, and then you have the distribution function fy here. Then the density function given by is this one. So if you look this one, you differentiate the capital Fy. You get small fy. Okay, so in statistics, capital Fy and small fy is different. Okay, capital Fy, usually we call it cumulative density function. Okay, this one usually we call CDF, cumulative density function. But Fy, we call it probability density function. So this is for continuous. If you remember, for discrete, you have PMS. Okay, PMF, probability mass function. So this one for discrete. Okay, but here we have PDF. So that's why we will have CMF. Okay, usually cumulative mass function, probability mass function. This one for discrete. But for continuous, capital F, you will have cumulative density function. Small f, you will consider probability density function. So from capital F, you want to get small f distribution like this, you must differentiate. Okay, that's why when you have small f, okay, small f, which is probability density function, when you want to get capital F, you must integrate. Okay, whereas f dot is the probability density function. Okay, again I mentioned, because you have small f, it's a density function, and t is used as the variable to integrate. Okay, so we can look example. Okay, this is the figure. Okay, so if you look discrete, in my previous explanation, you get it's a step function. Okay, but when you have continuous random variable, which is truly continuous random variable, you actually find the area under the curve too. Okay, so you can see you have, this is this density function, small fy, and inside here is a cumulative density function, and this y naught is a limit, it's an interval between 0 and y naught, for example. Okay, because we want to see the probabilities, for example, between 2, and 3, what is the probabilities? Okay. Then we have probability CRV. So CRV is continuous random variable. Okay, by theorem 4.2. Okay, we have properties density function. If Fy is a density function, so you can see if Fy is a PDF for a continuous random variable, then the density function greater than 0 for all y, where y between negative infinity to infinity. And then number 2, the integration between negative infinity to infinity of the distribution function should be equal with y, should be equal with 1. Okay, this is important. If you Okay, so now we look example 4.2, page 162. So suppose that you have this stepwise equation. Okay, you can see here is a capital Fy. So 0 when your y is less than 0, y when your y is between 0 and 1, and then 1 if your y greater than 0. So the question asks you, find probability density function of y. So probability density function is PDF, isn't it? And then denoted by small fy and graph it. Okay. So first of all, if you look this stepwise function, when you graph it, you have here capital Fy. Alright. And then here is you have 0, 1. So this is your y. So you can see that when your y is less than 0, it's here 0. When your y equal to 1 or 0, 1, you will have if you look here, when your y equal to 1, y greater than 0, it will be 1 here. Okay, here. So between 0 and 1, it will be y. So here is your y. And here when your y is less than 0, it's a 0. So this is for graph Fy. Okay. But now the question asks you to find PDF, which is small small f. Okay. So how to find it? So based on previous theorem, you should differentiate. So in order for you to get Fy, you will have differentiate 0 with respect to y, you get what? 0. You differentiate y with respect to y, you get 1. You differentiate 1 with respect to y, you get 0. So here for y less than 0, this one for y less than 0 and 1, here when y greater than 0. Then when you graph it, here you get y, here is your small fy. Okay, so basically you can see your y is 0, 1 as well. Okay, when your y is less than 0 here, what is the probability? 0. So it will be here. Okay, but when your y is between 0 and 1, you will get probability here is 1. Here is your 1. Okay, and then if your y is greater than 1, greater than 1 or greater than 0, you will get 0 here. Okay. Alright, so if you look the question back, example 4.2 ni, this one is 1, okay? No wonder lah. I think this one something wrong here just now. Okay, so that's why here will be 1 as well. Okay, that's mean if you have y greater than 1, here will be 0. Okay, so really sorry for this one. This is the mistake lah. Okay. Alright, so note here, in general, the distribution function for a continuous random variable must be continuous. But the density function not everywhere continuous. Okay, so you can see here, this one should be continuous, but then if you look your density function, is this continuous? No, not really. Okay, not necessary to be continuous. Okay, but distribution function should be continuous like this. Okay, now we look example 4.3. Let y be a continuous random variable with probability density function given by this stepwise function. Find distribution function, which is capital Fy, graph both Fy and capital Fy. So here, if you look example, given probability density function, PDF, okay, small f. And then they ask you to find distribution function and then graph. So look here, this one, if you graph the PDF function, you will have y here, 0 and 1, okay, because from y is 0, 1, and then elsewhere is 0. But here, if you look, 3y squared for y between 0 and 1. So let's say you put y equal to 0, you will get 3. Okay, here. When y equal to 0, you will get 3. And then if y equal to 1, you also will get 3. Okay, but elsewhere is 0. That means if my value y is negative 2, negative 3, negative infinity, I will get 0 here. Okay, if I have 2, 3, 4, 5, 6, 7, if my y is 2, 3, 4, 5, 6, 7, it will be 0 elsewhere, 0. Okay, so from 0 to 1, we have this equation. So that's why this is your equation. And then if you look here, this is square. Okay, if you remember, when you learn square, you will have this, isn't it? In this case, we have 3y square. So there is a square thing here. Right, so this is your fy. Right, now to find the distribution function, fy, so you need to integrate. Okay, do you remember from the previous theorem, when you want to find distribution function, you need to integrate, okay, from infinity to y, ft dt. Okay, that's mean here we have y, but we use t in order to integrate. Okay, so now we have fy. Okay, so you look here, we have less than 0, 0 until 1, and greater than 1. So for integration, you need to do that as well, because integration is a area under curve, isn't it? Okay, so that's why you will have first less than 0. So when you have less than 0, you will have negative infinity to y, and then here will be 0 dt. So this one you will get 0. And then you will have from infinity to 0, here will be 0 dt, okay, because you don't have the equation here. You only have from 0 to 1, okay. So plus 0 to y. So here 0 to y, you get 3y squared. So because we use t, we will have 3t squared dt. Okay, so this one when you integrate, the first part you get 0 plus this one you get 3t cubed over 3. This one is 0y. So basically when you substitute this value, this one can be simplified. When you substitute here, you get y cubed. Okay, y cubed minus 0, you get y cubed. Okay, so this one for 0 until y. Y between 0 and 1. Okay, and then next is for the greater than 1. Okay, you will get from here, which is negative infinity to 0. You get 0 lah, because you don't have function at fy here, isn't it? And then plus 0 to 1. So you can see 0 to 1, you get this one. So you have 3y cube, so not y lah, because we use t here. Okay, 3t square dt. Okay, and then plus from 1 until y, 1 until y, you don't have any equation, so you use 0 dt. Okay, so here when you substitute, okay, when you this one from 0 to 1, okay, from 0 to 1. So when you integrate this one, the first part you get 0 plus this one you get 3t cube 3, this one 0 1. Okay, and then plus this one you get 0. So here when you substitute, you get, what is it? This one you can simplify, you will get 1. Okay, so basically if you summarize, you will get this one. Fy will be, the first one is 0. Okay, 0 for y less than 0. And then you get y cubed for what? This one, y between 1, 0. And then this one 1 when y greater than 1. Okay, greater than 1. So when you draw the figure, okay, you will get here capital Fy, here is y. So you can see that when y less than 0, you get 0. Here 0. So here is 0, 1. Okay, when y between 0 and 1, you will get y cube. Okay, that means if you put 0, 0, if y 1, you get 1. Okay, so you will get here 1 as well. Here 1 as well. Okay, but then when y greater than 1, you get the same value 1. So here you have this graph. Okay, so that's how you do to find the distribution function. That means we integrate part by part. Okay, you can see the range. Okay, you must do by that. Okay, from infinity to 0, 0 to y, y until 1, y until infinity lah. Okay, and then this is the graph. So now look definition 4.4. Okay, let y denote any random variable. Okay, if you have p between 0 and 1, the pth quantile of y denoted by psi p is the smallest value such that the probability y is less than psi p equal with distribution function psi p greater and equal with p. Okay, if y is continuous, which is psi p, is the smallest value such that distribution function psi p equal with y less than equal psi p, and then you equal with p. Okay, some prefer to call psi p as the 100p percentile. Okay, of y. So here's something to do with percentile. Okay, p is stand for percentile. So first p is between 0 and 1. For sure, you can convert into 100 percentile. And this is a special case. If you have p equal to 1 over 2 or half, it means psi 0.5. And percentile you learned before, when you have half, that means you have median of the random variable y. So you consider the example 4.3. Previous example, the median of the random variable is such that distribution function psi 0.5 is equal with 0.5 and is easily seen to be such that actually you have cube. Okay, because we have y power 3, isn't it? Okay, if you look this one, so if you look, let me see, if you look our previous here, we get this one, y cube. That is our example 4.3. So that's mean if we have median, so it will give you the same p. Or equivalent that the median of y is psi 0.5. You will have 1 over 3. You get 0.7973. Okay. So this is special case if you have p equal to half, which is median. Alright, so you will have this link. This is the link. Okay. Alright, now look theorem 4.3. If the random variable y has density function fy and a less than b, then the probability that y falls in the intervals a and b is this one. Okay, this one you have done before. So this is the figure. Okay, this is the figure under curve. You can see y is your x-axis and your y-axis is fy. So we have curve and then we have between a and b. So in order to get this area, you will have fb minus fe. Okay. So basically you will have like this lah. FB, oops, sorry. So you have this one, FB, okay, minus FE. Then you will get this one. Okay, this is what we want. Okay, that's why sometimes we just integrate A until B. You get straight away, get the answer. Or you can have like this lah. Okay, now look at example. So example 4.4, page 165. Okay, given fy equal with cy square, y is between 0 and 2, and fy equal to 0 elsewhere. Okay, find the value of c which fy is a valid density function. So in order for you to know this is a valid density function, you must equal with 1, isn't it? So that's why you will have like this, f infinity for negative infinity to infinity, fy dy. This one should be equal with 1. Okay, so here you will get, okay, what is your fy? Cy square dy. What is it? From 0 until 2. So you differentiate it. This one should be equal with 1. So you differentiate this one, not differentiate, you integrate this one. You will get cy cubed over 3, 0, 2. So this one, what we will get? So here will be 2 cube, you will get 2 times 2, 4, 4 times 2, 8, isn't it? So here 8. Okay, and then here will be, okay, I'll show you step by step. So here, this one 2 cube. Sorry, this one should be C2 cube over 3 minus C0 cube over 3. Okay, so this one actually 0 lah. So here you get 8 over 3 C. Okay, so now you want to find C. Okay, what is C? So this one equal to 1 just now, isn't it? So 8 over 3 C equal to 1. C will be, this one you get 3 over 8. Okay, but you must understand your integration, okay, the part of integration. So now we look at example 4.5. Find probability y between 1 and 2 for example 4.4. Also find probability y between 1 and 2 exclusive. Okay, so from example 4.4, you get your C is equal with 3 over 8. Okay, basically if you write down this one, you will get fy equal with 3 over 8 y square, y between 0 until 2. So here example 4.5, you need to find probability y is between 1 and 2. Okay, so actually you will have the same distribution density function here, but you will integrate from 1 until 2 fy dy. Okay, so fy is this one, you substitute here. So basically the constant, you can bring it out, 3 over 8, and then you will have y cubed over 3, 2, 1. Okay, so this one you will get 3 over 8. 2 power cube is what? 8 over 3 minus 1 over 3. So here you will get 3 over 8. 8 minus 1 is 7 over 3. So you can simplify 3. Finally, you get 7 over 8. Okay, so that's the answer for the probability y between 1 and 2. And then, how about this one? Okay, basically, if you look from previous, you have p y equal to 1 is also p y equal to 2 is equal with 0. Okay, so therefore, you will get the same things like this. Okay, you will get the same thing like this. Okay, but instead of you have equal sign here, you don't have equal sign. Okay, because y has a continuous distribution. Okay, it doesn't matter either included or not included, you will get the same things, the probability. All right. Okay, so now this is the exercise. So make sure you try all the exercise, okay, especially what I asked for in the slide. Okay, and extra exercise you can go through all from your textbook. Okay, so thank you class.